Hello everyone and welcome to your first tutorial on climate modeling. In these first few tutorials, we're going to primarily focus on energy balance, which is the foundation for all climate models. You already learned a great deal about this from our keynote speaker, Brian Rose, but in these tutorials, we're going to build on this concept and you're going to learn how to construct a model of energy balance on a computer. Finally, in our last few tutorials, we're going to discuss more complex models. But first, let's define what we mean by energy balance. So energy balance is when energy coming in is equal to energy going out. In terms of Earth receives and is heated by radiative energy from the sun, called insolation. This is short for incoming solar radiation. Some of this insolation is reflected off pale surfaces, such as ice, snow, and clouds. And then the remaining portion is absorbed somewhere in the Earth system. Earth then warms from this absorbed shortwave radiation and re-emits its own energy back to space called outgoing long-wave radiation, or OLR. In this tutorial, we're going to focus primarily on how Earth loses energy to space, its outgoing long-wave radiation. In the next tutorial, we'll cover how Earth gains energy in more detail. And then finally, we'll piece these two together and describe energy balance as a whole. So first, how does Earth lose energy? Well, one mathematical model often employed is Planck's law, which is the first equation on the right here. Planck's law is dependent on both wavelength and the emission temperature of the object. This equation is plotted for several emission temperatures on the left, and these emission temperatures surround Earth's global mean surface temperature of near 288 degrees Kelvin. And if we look at these curves in a bit more detail, we can see that the peak of these curves moves to the right towards longer wavelengths as the emission temperature gets lower or colder. And this is mathematically defined by Wien's law, given as a second equation on the right here. And this tells us that the peak emission wavelength is inversely proportional to the emission temperature of the object. And so, for example, for a black body with an emission temperature near the sun, say 5,800 degrees Kelvin, the peak of that curve would be so far to the left, it would be basically distinct from the curves of these colder black bodies given on the slide that are more similar to Earth. And this is why we call Earth's radiation outgoing long-wave radiation, and we call the radiation from the sun incoming short-wave radiation. Additionally, note that for higher emission temperatures, the curve lies strictly above that of lower emission temperatures, which suggests that hotter objects emit more energy at all wavelengths. And so if we integrate Planck's law over all wavelengths and account for all the outward emission angles of Earth's surface, what we obtain is the power radiating from a unit area. This is called the Stefan-Boltzmann Law. It's given as the equation on the right, and the constant sigma is called the Stefan-Boltzmann constant. Note that this is a per unit area measurement, and this is the quantity we are interested in when assessing Earth's energy balance in future tutorials. And while we assume that Earth emits approximately as a black body, the radiation that actually makes it to the top of the atmosphere is much less than it should be based on the theory we just covered. And this is important because the top of the atmosphere is where we calculate our energy budget. And so this is shown in the figure here on the left in the top panel, where the actual energy reaching the top of the atmosphere is given by the blue shading. And then on top of that, there are some black body curves plotted as well, with various emission temperatures ranging from 210 to 310 Kelvin. And what we notice is that none of these are a particularly good fit for the blue shaded region, and that there are many spectral gaps. And this is because the simple model that we just examined does not take into account that Earth has an atmosphere. And within this atmosphere are gases like carbon dioxide and methane and water vapor, which absorb radiation at the wavelengths that Earth emits at infrared band. And they re-emit energy back towards our surface to be absorbed and re-emitted by our surface, and so on and so forth. This is called the greenhouse effect. It's one of the things that's really responsible for keeping Earth a habitable planet. And so a first approach to incorporate this into our simple model is to add a coefficient tau, which is a number between 0 and 1, that effectively reduces the amount of outgoing long radiation that's seen at the top of the atmosphere due to absorption by greenhouse gases. And this is the first parametrization. You will use And it's a parametrization because we don't explicitly incorporate each individual gas and the related processes into our model, but rather we represent the effects of all of these gases with a bulk coefficient. In this tutorial, you're going to estimate this coefficient, tau, from observations, and in the next tutorial, we're going to move forward to where we'll discuss how Earth gains energy from the sun. I'll see you there.